All right, it's me again. So my second talk is also a group talk. So I'm taking my breeding team here too, but it's a partial team. We have 3 other people who are not coming. So I'm going to talk about the varieties we develop to improve the grower profitability. So that's our goal. So me and my PhD student Zhang Shea and postdoc Dr. Zhibo Wang and William Singer, he's my other PhD student, but he's not here today because he got exposure of COVID, a positive COVID case on Saturday. So as a public breeding program, we serve for Virginia and the Mid-Atlantic region. And we develop elite cultivars using classical breeding methods and the novel breeding technology, including CRISPR-Cas9, the gene editing technique. And Zhibo is going to talk about our CRISPR project later. So here I'm listing the major breeding objectives. The first one is we develop herbicide-tolerant and conventional soybeans for Virginia and the Mid-Atlantic region. And Dr. David Holzhauser mentioned the extended flex. So I had a talk with Bayer Crop Science 2 weeks ago. So we start to make the paperwork so we can use their extended flex donor in our breeding program. Several years ago, we also got the Liberty Link paperwork. But after so many years of trial, I just couldn't find any Liberty Link cultivar making me confident to pass them to growers because the donor, with the Liberty Link donor, our breeding lines are so tall, like forage soybeans. I just couldn't really, using back crossing, to make any Liberty Link cultivars available for the Virginia growers. But we will try the new thing, the new trait, the extend flex. And then we also incorporate value-added traits into specialty soybeans to reinforce the Virginia growers' competitiveness in the various soybean market. Number 3 is we develop diverse germplasm, the diversity in like maturity groups, like David Holzhauser mentioned it earlier, maturity groups 3, 4, and 5, and pest resistance, stress tolerance, like Dr. David Lanston mentioned. We need to have more resistant genes, not only use PI88788 or Peking source for 6 nematode. We need to have some other newer diverse genes into the disease resistance. For this developing diverse germplasm is to broaden the genetic background of soybean. Number 4 is we are using modern breeding techniques to improve seed compositions, to improve the soybean quality, protein quality, and oil quality. And here I have 3 circles here. I show this a lot to my students. This is 3 concepts of my breeding program. The first one is we do applied studies. We do not really do many basic studies, but because we need to apply our results in the production, the benefit to grower stakeholders. Number 2 concept is economic impact. All the projects we're doing must have strong economic impact. The third one is we're student-oriented. So we provide extensive training to graduate students and undergraduate students to make sure they can move forward successfully to the next step in their own career. And here's a picture showing USG 5618V. We released in 2016. It's still a popular conventional soybean cultivar. So when we talk about the release, I started in 2013 at Virginia Tech. So the first release was in 2016. So from 2016 to 2021, we had 12 releases, and 7 of them are privately licensed to private companies, one a long-term collaborator company, and then regional seed companies, and recently one cultivar was licensed to a national company for their poultry production. And we do have the list over here, and we have more conventional and specialty soybean released than the transgenic, like with technology traits, because our strength as a public breeding program, Our strength is more on this conventional value-added traits. And here's a picture you may not recognize. It's tofu. So when I was in Japan, I think 2017, I tried this tofu because it's made by Virginia Tech cultivar called a MFL2P59. So that tofu cultivar has been very popular in Japan's tofu market. So when I tried this hot, fresh tofu made of Virginia-grown soybeans, and from my breeding program, I was really proud of our breeding program. And next year, we should have about 3 to 4 food-grade soybean release. And I talked to Tom Tolliver the other day. I said, do you have any impact or effect by the COVID for your business? And he was smiling to me. He said, positive. I said, that's great, because we will release more food-grade soybeans for the food-grade soybean industry and the overseas market. And we're going to talk more about one trait, test weight, because farmers really interested in the test weight trait. And we have 2 more seed compositions. One is trypsin inhibitor, one of the anti-nutritional factors in soybean. Another one is methionine, is one of the essential amino acids in soybean seeds. So Zach, it's your turn about test weight, and then Jibo, trypsin inhibitor, and then Zach come back again talking about methionine.
Hey everyone, like Dr. Zhang said, my name is Zach Richet and I'm a PhD student currently at Virginia Tech working with test weight, but today I'll also talk about methionine because my coworker cannot attend, unfortunately. So for those of you who don't know, test weight is the amount of soybean in pounds that fits into 1 bushel and is one of the primary indicators of soybean seed quality. Every crop has a standard value for test weight, and the standard value for test weight is around 60 pounds per bushel. Now test weight is important because soybean with higher test weight is generally more durable, better for transportation, lasts longer in storage, and is less prone to getting mold. Now, I know it's probably difficult to see in the back, but these 2 pictures show soybean with a high test weight, which is over on this right, and then one with low test weight, which is over here on the left. After the talk, we're going to come up and take a look at them, but just take my word for it. Besides just looking better, the one with higher test weight is also more durable and better for transportation and storage, like I mentioned earlier, but it can also go for a better price when, sorry about that. It can also go for a better price when compared to soybean with lower test weight. Additionally, test weight can affect pricing because if it falls too far below that standard value, you can receive a pricing penalty. This limit for you can start to receive a pricing penalty in soybean is around 54 pounds per bushel. Another point of interest is that test weight has been decreasing over time. This graph over here shows test weight values from the 1950s up until about 2015, and as you can see, there's been a slight decreasing trend over time. So back in the 1950s, growers were seeing more values around 60 pounds per bushel, but now they're seeing more values around 56 pounds per bushel. While 56 pounds per bushel is still good, it's starting to get closer to that level to where you can receive a pricing penalty. This is important because if this trend continues, eventually growers will start to see pricing penalties a lot more frequently. Thus, the focus of this project was to gain a better understanding of the components in soybean that affect high test weight by identifying genetic markers associated with high test weight and by determining the relationship between important seed composition traits and high test weight. The seed composition traits that we looked at for this project specifically were protein, oil, and sugar content. In order to measure test weight, we used the 2500 UGMA from Dickie John. To measure protein and oil content, we use NRS, and to measure sugar content, we use HPLC. Also for this study, we grew a population of diverse soybean accessions that originated from many different countries in 2 locations in Virginia, Blacksburg and Warsaw, Virginia. We were able to identify multiple markers associated with high test weight, but the markers that were important depended on which location you were in. So the markers associated with high test weight in Blacksburg were different than the ones associated with high test weight in Warsaw. With this said, we were still able to use this information to select for parents that have these markers and use them in our breeding scheme to hopefully develop new varieties that will continue to have high test weight. Additionally, we found that protein and oil content were significantly negatively related with high test weight in both locations, but did not have a significant relationship with sugar content in either location. This could imply that by selecting for increased protein and oil content, you can negatively affect test weight and soybean seed quality. This could partly explain the decreasing trend in test weight that we've seen over time, because one of the main objectives for soybean breeding is to select for varieties that have increased protein and oil content. Thus, by intentionally selecting for increased protein and oil content, we could have been unintentionally selecting for decreased test weight. So to wrap everything up for test weight, by identifying genetic markers associated with high test weight and by determining the impact or the relationship between test weight and important seed traits, we will be able to improve our breeding scheme to hopefully develop new varieties that will continue to have high test weight to ensure your profitability. And I'll turn over to Zhabo to talk about trypsin inhibitor now.
Everyone, my name is Zhibo Wang. I'm a postdoc working for Dr. Bo Zhang. And today I will talk about my project. It's a trypsin inhibitor. Trypsin inhibitor is one of the major anti-nutritional factors in the soybean, and it can cause the low efficiency of protein digestibility when the soybean meals are fed to animals. And in the processing, so the trypsin inhibitor can be deactivated by the heating process. But the heating process can cause the reduced nutritional value, and also can cost more money by 25% more. So, and in the soybean seeds, there are two genes. One is TI1, another one is TI3. They mainly contribute to the trypsin inhibitor contents in the soybean seeds. So, in order to kick out these two genes very quickly at one time, so we introduce our gene editing approach, CRISPR-Cas9, the novel new technique to speed up the breeding process, because we want to get a very low TI variety, so we don't have to do the heating process. It can save us money, and it can also keep the nutritional value for the soybean seeds. And after application the gene editing technique to natural variety VDM82, we got four mutant lines. And for the KTI1, you can see here a large fragment lost in all four varieties for KTI1. And for KTI3, in the first three mutant lines, so a large fragment also lost. And for the last mutant line, the fourth one, so there is insertion there, but also has a large deletion there. So we suppose, so for KTI1 and KTI3 in our four mutant lines, the two genes should have lost their function. And then we measure the trypsin inhibitor contents in those four mutant lines, compare with our natural mutation, VDM82, those four lines, mutant lines, the trypsin inhibitor contents dramatically decrease. So that means it works very well. And in the future, we want to use these four mutant lines for the crossing as parental lines. So that's me. So yeah, sure, of course you have.
How much healthier is cold extruded oil versus heat extruded oil?
I'm sorry.
The oil that you get from cold extrusion, which you can put the trypsin inhibitor into the genetics of the soybean versus a heat extruded oil.
How much? So I think the question is, if we develop cultivars with low trypsin inhibitor. I think the question is, if you use heat to deactivate trypsin inhibitor versus you develop a low trypsin inhibitor breeding lines, right?
When you're extracting the oil, when you're extruding the oil from a cold process versus a heat process, because of the trypsin genetics and the adverse effects of the dealing with the trypsin.
I mean, the digestibility, if you process with cold instead of heat,
Yes.
the trypsin inhibitor, most of the trypsin inhibitor will still have strong activity in the cold processed beans. So it's like if you feed the animal with the high trypsin inhibitor soybean seeds, they cannot really digest, because the trypsin's function is to break the large protein molecule into small protein. If we eat raw soybeans, we cannot digest either. This is a natural defense of soybeans, because the soybean seeds are in the field. The deer eat the plants, but not the beans, because they cannot really digest the beans. So that's the soybean's natural defense system. Yeah. So for this CRISPR-Cas9, because the natural defense system, we still want the leaf of the soybean plants keep this defense system. So the insects do not want to eat the leaves because the leaves still have trypsin inhibitor in there. So we only target to edit the gene in the disease. So we have still high trypsin inhibitor in the leaves for the other organs of the plants, tissues of the plants, but we have low trypsin inhibitor in the soybean seeds. For the traditional breeding techniques, we cannot really say we can edit the gene in that tissue. We do not edit the gene in this tissue, but with CRISPR-Cas9, we can really target which genes we want to target. And for KTL1 and KTL3, these two genes, they do a lot of function in the seeds. They have nothing or little function in other tissues. That's why we target these two genes. And for the figure down on the bottom, if you cannot really see, but the long one, that's trypsin inhibitor content in a natural soybean. And on the top 4 really short bar, that's trypsin content in our edited breeding lines. So you'll see the big difference and how the CRISPR-Cas9 really work on the soybean gene editing system.
So maybe I can give you more comments. So the trypsin inhibitor per se, it's a protein. So the protein can be still active, in the cold or normal temperature, but a heating process can just destroy the 3D structure of the protein. Just like you boil the meat, kind of that. So the cold, I don't think it does work to deactivate the trypsin inhibitor, but for the heating process, it can deactivate the trypsin inhibitor. But heating process definitely will cost more money, right? And another thing, another point I want to mention that, so because those gene editing, based on this information, we also develop some selection markers for the future breeding. So in the future, you can use just our parental line, and then after crossing, so we can provide our selection markers, and with selection markers, you can easily identify which one is the low TI one, which one is the just normal one, and you just keep the low TI one. So with this way, with this direction, you can stack different human beings' favorable traits very, very quickly. Yeah. So that maybe.
Yeah, one thing to add. Process, the energy is not only the money problem, because if you overheat the meal, you really destroy some amino acids and reduce the quality of the protein. Because there's a quality control process, but if your temperature of heating process is low, there's still trypsin inhibitor left in the meal. They still give the negative effect of the soybean meal to the animals. So how to control the temperature just right is hard to do, but with the low trypsin inhibitor soybeans, you can do it.
Hey everyone, me again. So as you have probably heard throughout all this morning, soy is very valuable economically speaking. Currently in the US, soybean protein is the driving factor of its value, representing about 70% of its seed worth, with 97% of all meal being used in livestock feed. That other percentage of soybean protein is used in a variety of food ingredients that we've kind of heard about today, so like tofu, edamame, soy flour, and textured vegetable protein, as well as some other things. Additionally, there's been an increased market for plant-based protein for human consumption that has led to an increased demand in soy products. Therefore, many resources have been allocated to improve the production, efficiency, and nutritional value of soy in regard to food and feed. However, there have been limited work done looking at improvements in the amino acid profile, which is the true nutritional value factor that Dr. Bo had mentioned earlier a little bit, in conventional varieties. Additionally, while there are some nutritional differences in the nutritional requirements between livestock and humans, there are 9 essential amino acids that are required by all livestock and humans. This makes soybean protein a valuable food and feed ingredient because it contains all 9 essential amino acids, with methionine being one of them. Despite this, the most significant nutritional limitation in soybean is its methionine deficiency. Methionine is also one of the major growth limiting factors in the poultry industry, which consumes about 55% of all soy meal in the US. To overcome this obstacle, many processors and producers have started using supplementation and rationing. While supplementation is an easy solution, it has many downsides, including hazardous waste production, poor livestock nitrogen use efficiency, and potential nitrogen waste output. Despite the importance of methionine in soybean, there are few varieties available that have increased methionine content. Additionally, there's been limited work done looking at the impact of sulfur-containing fertilizers on methionine in soybean. Thus, the focus of this project was to improve soybean protein quality through increased methionine content by identifying genetic markers associated with high methionine and by determining the impact of fertilizers on methionine. In order to identify genetic markers associated with high methionine, we conducted a 2-location study over 2 years and grew our populations in Blacksburg and Warsaw, Virginia. This picture, it's a shame, it's too small to see, but it shows some of the plots growing in Blacksburg over in Kitland Farms, and they look really pretty right now. So if you want, afterwards, I highly recommend coming up and taking a look at it. But we were able to identify multiple markers associated with high methionine, and we are currently using these markers to select for parents that have them and using them in our breeding scheme to develop varieties that have increased methionine content. In order to determine the impact of sulfur-containing fertilizers on methionine, we conducted a 6-location study looking at the effect of 4 fertilizers: ammonium sulfate, or AMS, ammonium thiosulfate, elemental sulfur, and calcium sulfate, or gypsum. Now, we also looked at the impact of application rate on methionine, and we looked at the application rates of 0, 10, 20, and 30 pounds per acre. Lastly, all fertilizers were applied pre-planting. Our results did vary greatly between locations, which wasn't too surprising given that environment does have a huge effect on methionine, but of the fertilizers tested, we found that only one, AMS, had a significant effect on increasing methionine in soybean. The others were found to not be as important. Lastly, we found that application rate didn't really affect methionine in soybean significantly. And so now, while we are starting to gain a better understanding of the impact of fertilizers on methionine, there's still some more work we can do in the future. One aspect we have reason to believe that can significantly affect methionine is looking at the timing of application. For this project specifically, we only applied fertilizers pre-planting, but in the future, we could look at the difference in applying fertilizers pre-planting versus post-planting. So to sum everything up for methionine, by identifying genetic markers associated with high methionine, we can develop new varieties that will have increased methionine content, and by determining the impact of fertilizers on methionine, we can help make more informed management decisions to lead to the improvement of soybean protein quality through increased methionine to ensure your profitability. And that concludes everything for methionine.
Schedule, but the research that where Zach and Will got beans from was my research, and we actually did. Thank you for explaining my research. We had 4 sources and 4 rates as well. And so we wanted to know if sulfur was limiting in the mid-Atlantic sandy loam soils. And so we had 6 sites. You can see, hopefully this map is big enough, all across the mid-Atlantic region in Virginia. There are lots of mixed results, same with the methionine research, but what we came up with was we didn't necessarily see a source impact. We did look at timing, but didn't send those seeds to Blacksburg to get analyzed. We didn't see a very big difference in timing. What we did see was rate, and that was variable across the whole map. And so a safe bet, I would say, just to sum it up, would be about 10 pounds per acre. We saw some yield increases with sulfur, but as we increased to 20 and 30, 6 out of the 10 sites saw decreases in yield at 30 pounds per acre. So this is something that we need to look deeper into. Why is that occurring? What is actually happening in the soil? And also be very intentional with how we are applying the sulfur, what we are recommending. So that's the small bit, just not to take up a whole lot of time. Are there any questions?
I just want to make a comment, just to give her some credit. Karen has volunteered to analyze sulfur research from how many states? 5 to 10 states.
I think it's more, yeah, it's more than that.
She volunteered. I'm not sure if she volunteered or Dr. Ryder volunteered for it. Actually, I'm the one that mentioned her name to our working group in the U.S., but I want to say thank you for doing that, because unless we get that data out and get it analyzed, it'll be not a lot of use. They are seeing responses in some parts of the U.S., other parts not. So.
Yeah, and that's the crazy thing. In high clay soils, they are seeing more responses than we are seeing here in sandy soils. And so I think that's where we can get the big picture with the multi-state study, kind of like you were talking about with the varieties, looking at the whole picture.
Also appreciate the methionine work, because that, again, that's the real amino acid, even though soybean have it all, that's really kind of kicking soybeans' butt, as a good feed additive. So it's,
And thank
that
you,
work's gonna
Dr.
be real valuable as
David
well.
Holzhauser, because this methionine work has been done by Will Singer, and David is Will Singer's committee member. So when we had our meeting, and David mentioned, oh, we have a trial. Maybe you can use your Sulfur trial seeds to work on methionine. So that's a...
Yeah, I like to create work for other people.
I know one more comment for the methionine and sulfur application. So because the methionine is the first amino acid, always the first amino acid for all proteins. So because the ribosome always recognizes the codon for the methionine, so methionine is always the first amino acid for all proteins. So that means methionine regulation must be very, very strict. So what I want to say is, just apply some sulfur fertilizer. Maybe it's one reason why it cannot increase the methionine content, because soybean or other biological systems want to regulate this synthesis of the methionine very, very carefully.
Thank you, Zhibo. I know we ran out of time, Joseph, but I want to mention our team, because we're having Zoom meetings all the time. Now we're taking pictures on the screen, so like screenshot with the team. And then Montague Farms fund us to do the food-grade soybean breeding, and Virginia Soybean Board always give us tremendous support since I started. And from 2014, Virginia Soybean Board fund us the trypsin inhibitor project until now. I think it's still going on. And also our entire breeding program supported by Virginia Soybean Board. And VCIA, Tom was really generous. Maybe the other day he said, Bo, remember you have account. You have money in our account. Let me know whenever you need money. So thank you, VCIA. And VDEX. VDEX supported us on edamame research and soybean sprouts research earlier. I mean, the edamame research is going on right now. And Ag Council is very, very, very helpful too. Recently, Ag Council is giving us money to do a feeding trial. And Zach, actually, he's working at the seafood area in Hampton this semester to use rainbow trout, right, the fish. And yeah, and use our own cultivar, process into the meal to feed the fish to see the growth rate, those kind of parameters for aquaculture. And the college all the time support us. And overall, I think all this, everybody on the poster, we cannot say enough to appreciate the support and the help, and keep us in program running sustainability, right? Yeah, sustainable in the financial. Right. Thank you all very much.